In this video, we'll learn about continuous random variables. We'll be referring to content from Chapter 5 and some of Chapter 6 in this lesson. We'll begin by getting the idea of what a continuous random variable is and a distribution that goes with a continuous random variable. And in following lessons, we'll get more in depth and do more examples. So continuous probability distributions are for random variables that are continuous or that are going to take on values that would be on a continuous scale, such as heights of radish plants. Let's review the difference between discrete. We've been working with discrete random variables and their distributions, and now we want to think about the difference between that and what we're about to do with continuous. So discrete are usually things that are counted, and there are gaps between possible values. So you can actually go between any two possible values and not have anything in between. Whereas continuous random variables are things that are measured, and no matter what two possible values of the random variable you pick, you can always find another one in between, and that's because there's an infinite number of possibilities. It's a continuous scale with no gaps. So remember with discrete probability distributions, and these were also finite. Discrete doesn't always mean finite, but in the examples we were doing, we had discrete and finite examples like rolling a die and counting the number of dots on top. There was only 6 possible things that could occur, and so we could list them out and list their corresponding probabilities with each possible outcome and see that those probabilities all added up to 1. Since we wanted to make sure we included every possibility, we didn't overcount and we didn't undercount. Well, that's just not going to work anymore. We would never even be able to write down all the values that the random variable could be when it's on a continuous scale. So we won't be using tables anymore to represent a distribution of the probabilities. Instead, we'll be using distribution functions, which you might remember the concept of a function from algebra, where you would graph a curve that had a function, or you might think of it as an equation where you could plug in an x value and get back a y value. Or you could plug in a horizontal location and find a corresponding vertical location. So that is the curve we represent with f of x, meaning the probability of x in theory. But we create a curve like this, and if this curve represents the probability of x, and I go to any one x value on the axis and go up to that curve to find the probability, the truth is that the true probability is going to be 0 because there's an infinite number of possibilities, and the likelihood of landing on 1 out of infinity is 0. So we don't find probabilities for an exact number of successes anymore. Notice that the total area under the curve should be 1 because now area, shaded area, represents the probability. So if we're covering all the bases, then all the areas should add up to 1. And like I said, we're not going to calculate the probability of a single x value. We're going to calculate the area under the curve between any 2 points, or below a point, or above a point. So these are cumulative probabilities. So 2 things: the probability density function is what draws the curve. The cumulative distribution function is connected to the areas under the curve. So the curve, the PDF, is used to describe probabilities and how they are distributed over the entire range of possibilities. So if x is continuous, then the probability density function f of x is used to draw the graph of the probability distribution. And the cumulative distribution gives the probability as an area. The total under the curve is 1, and we can denote cumulative probabilities in this way, which means the cumulative probability of x falling between A and B, or like this, the cumulative probability that x falls below A, or like this, the cumulative probability that x falls above A. So that's the introduction for the most part. I'm just going to talk about a couple of continuous probability distributions that we're going to learn about in more detail. And there are many kinds, so many that I couldn't possibly even list them all. But there's two that we're going to focus on in this course. The uniform distribution, which only makes a brief appearance in the grand scope of our course, and the normal distribution, which stays with us for the remainder of the course, and it's the basis for pretty much everything else we do from here on out. So in the next video, we're going to get more into detail on the uniform distribution, and then following that, we'll start to dig into the normal distribution. And this is going to be a continuing building process of understanding what the normal distribution is, how we can use it, and yeah, that's pretty much, I guess, all I need to say about that. Now, I'll just quickly say two things to remember about the normal distribution and the uniform distribution is the shapes. Normal distributions are bell-shaped and symmetric, and you have the mean in the center. Uniform distributions are called uniform because the probability density function will be just a straight line showing that the probabilities are laid out uniformly. They tend to be equally likely, all these values. Okay, so we have bell shapes to find areas under the curve, and we have rectangles to find areas underneath the curve. I know it doesn't look curved, but when we say curve in general, we mean any line that's drawn above the x-axis. So we'll see you in the next video to get more in depth on uniform distributions.